Okay, perfect. Um, okay, yeah, so I'm Sebastien Crozet. Thank you all for being here for one of the very last presentation of this event. So my goal here is to talk about WGML, which is probably something you've never heard before because I started this project about a year ago. And you have the GitHub link right here. My objective is not like to describe like the WGML API and how you use it, because you can just go to the GitHub repository and start reading the code. My goal here is more like to tell the story of how I built it, and in particular give you like the resources that I found helpful, so that if you want to do the same, and if you want to start your own framework, you have like some tools I found very interesting. So first thing, there are a lot of links in this slide. So if you want to click on them, you can just grab the slides here. Okay, so what's WGML? So if you are familiar with the LLM ecosystem, you probably know about a library named GGML. So WGML is kind of the concatenation between the W of web GPU and the GML of GGML. So basically, let's rewrite something like GGML or DMSCPP, but targeting the web GPU standard. So web GPU, if you haven't really heard of it, but I think now you have with the previous presentation, it's an open standard for GPU compute, which aims to target every platform. So it will also allow you to run GPU compute on the web. And it's not just compute, it's also for rendering. So you have a very nice API which allows you to do both compute and rendering in the same API. So you have some very efficient communication between the two. But in our case, we are purely on the compute side, but we will see that WGML being based on like being part of the larger WG math ecosystem, there is also some effort which communicates with rendering. So let's start with a quick demo here. So if you, okay, I have it here. So if you go to the wgmat.rs repository website, what you will see here is a bunch of demos, and you can select the WGML demo. So as soon as you loaded this page, which is like a WebAssembly application, you don't need the internet anymore. Like this is completely local, running locally on your browser. So you can, there's some recommendation of models you can load here, because this is running on WebAssembly and we have memory limitations on WebAssembly. It's limited to some smaller models. So if here I go and I open this one, which is DeepSeek R1 distilled with 1.5 billion parameters and quantized with Q4KS, I can open this here. It's loading. Okay, and then you have something very simple with like the metadata of your GGF file and like some information of your tensors. So you can provide a prompt here, you can submit the prompt, and then you wait and you will see your LLM running. So because this is like a DeepSeek R1 distilled model, it will have two phases. So you will have the first reasoning phase, and then later you will have like the actual response you are interested in. And on the bottom here, you get the performances. So here it's running at about 44, 45 tokens per second. And if you wait a little bit more, what you will realize is that the performance tends to lower a little bit in time. So now it's done with the reasoning part here, and it's writing down the kind of conclusion. And I think it's almost done. So at the end, we are about 50 tokens per second, and we generated about 2,500 tokens. So if we compare this with something like transformer.js, which was, I think it was open source like a few months ago. They also use the same model, so it's also DeepSeek R1 Qwen 1.5 billion parameters. And if you look at the source code, it's also using the Q4 quantization. So So I can load the model and I can type the same thing. Okay. And we run play. What you will see here is that we did start at a quite higher token per second, but as the context grows, performances will drop quite a lot also. So we can wait a little bit, but what tends to happen with this specific implementation is that it will loop indefinitely in the response, but maybe it won't. Let's see. Yeah, okay. So it will loop indefinitely with this like chocolate chips thing. So we can just pause that. And what we see here is that we are at 1400 tokens and we are down to 44 tokens per second. So in terms of performances, what we see here is that WGML is actually quite competitive compared to the Onyx Web runtime here. And the observation is that we are like slightly slower at the beginning, but as the number of as the context grows, our performance tends to drop more slowly compared to the transformer.js implementation. Okay, so that's like a basic demo. This application is not like the end goal of WGML. This is more like a tool that I'm using for showcasing and for testing the implementation. Right. So let's get a bit of context of what this talk is about. So let's say you are in the same situation as me, like about a year ago, and you are tasked with implementing a new high-performance local inference system that runs on every platforms and also on the web. But you're not like an AI expert. Like before, I didn't know anything about LLMs, so I had to learn everything from scratch. But of course, I did have a good grasp of linear algebra. But even if you don't, I suppose the only operation you need to understand is matrix multiplication. So that's quite fine. And I really didn't want to rely on a particular proprietary ecosystem like CUDA, but I also didn't want to follow the same approach like DGML, like Candle, which is to have to implement as many backend as you have targets. So that's why I choose Web GPU, so we can really target every kind of GPU platform. Now, of course, in the future, I'm really hoping that I can start using something like Slang for targeting even CUDA if I wanted, or even the CPU. So that's kind of on my list, but not started yet. So, okay, let's say you are in this situation. Where do you start? Well, first thing, of course, it's to start to learn about LLMs. And two of the best resources I found was this YouTube channel from Umar Jamils. So you will get a very, very nice presentation about the transformer model and the Llama model specifically. And you will see that this did play like a key role in my implementation. And then you can read some code. You can refer to llama2.c, which is very interesting because in a single file, you get all the implementation you need for llama2. So it's a very good point of entry. And it also has quite a few ports in different programming languages, if you are not familiar with reading C. And then you can go one step further and start looking into like the big players like Llama CPP, and you will see that it's extremely difficult to understand these kind of code bases because you have huge files with tens of thousands of lines of codes to parse. So if there were three things I would hope to have found right away is like the metal shader, so the MSL shader for macOS, which includes everything. So again, 10,000 lines of code in a single file, but you do have all the matrix multiplication variants, you do have like dequantization here, you have everything. And also having a good look at how the transformer is constructed is quite interesting because it gives a very good idea of what you need to do in terms of chains of operations. You can get familiar with running local implementations, so running Llama CPP, for example, because when you are writing these kinds of system starting from scratch, from nothing, you will have a millions bugs. So in order to debug that, one of the best way of doing that aside, unit test for every single of your operations, what you can do is to compare step by step with an existing implementation. And finally, if you are working in Rust, here are two open source projects that I found also very handy because they provided some parts like the chat loop, if you're not familiar with how that works, and also a bunch of shaders from WebLLM. Right, and also, yeah, of course, the GGFI format, if you really don't know anything about LLMs like me, well, that's one of the very easiest file format to parse and to read, and also one of the most popular. So I do recommend just implementing a parser for this format, and you will very quickly understand what a transformer is made of. All right, so you're done with learning about all the theory. Now you can start coding, and the very first thing I found relevant to do was to start with a CPU implementation, because the CPU implementation is what's the most easily debuggable. And what I did, and what I hope will be helpful for the community here, is that I did make a CPU implementation of Llama 2, and all of the steps of the implementation contain timestamps to the video, like the YouTube video for Umar Jamil. So that way you have a direct one-to-one matching between the theoretical explanation and the practical implementation. Yeah, there are some parts which are particularly difficult and not very interesting, as they might not run on the typically run on the GPU, and that would be the tokenizer and the sampler. So there are very, very good open source libraries for that, and in particular for the tokenizer, there is the very popular tokenizer library from Hugging Face. In terms of operations, what you need for Llama would be this set of operations. So it's not that much. The main ones would be matrix multiplication. You do have to be careful that some of your matrices might be quantized, and not all matrices will be within the same GGF file will be quantized with the same format. So you really have to be careful about that. Vector sum, that's straightforward. And then you have a bunch of kind of more AI-specific operations. So the reason why I'm saying AI-specific operation is because WGML is part of the WGMath ecosystem, and we will see more about that at the end of the presentation. But basically, matrix multiplication can be used for everything. Like it can be used for physics, for cohesion detection, for, I don't know, sound synthesis. So this is actually part of a different library within the WGMath ecosystem, whereas these operations here are more AI specific. So these are part of WGML, and these are specific shader which are not expressed in terms of matrix multiplications. Right, so let's say you have implemented everything and you tested it and it works well. You will need to check your performances, because of course your naive implementation will be very slow. So that demo I saw at the beginning, at first I was at about 4 tokens per second with my first initial implementation, which is of course, yeah, it's not good. So by looking at where the bottlenecks are, there were 2 things which kind of have a different consequence on the performances. The first one is matrix multiplication, because of course that's what you do 90% of the time in your transformer. And the second one was the attention mechanism, because I did have a naive shader which allowed you to run the attention in a single kernel invocation, but in exchange you could really just run this shader with a single work group. So it was very naive, and that one, instead of like just slowing down the inference in general, it will tend to completely break your scalability based relative to the context size. So as you get more tokens in your context, your performance tends to drop dramatically. So even after optimizing matrix multiplication, I was about like 40 tokens per second at the beginning, but after just 100 tokens generated, I would drop down again to 4 tokens per second. So that was because of the naive multi-head attention implementation, which I then rewrote in terms of tensor operations. So I only had to really optimize matrix multiplication. So let's talk about matrix multiplication optimization. Now, of course, you can spend about, I don't know, 10 lifetimes trying to optimize this. So here, my goal is not to tell how you can optimize this like to the bit, but more like this one optimization, which is fairly easy to implement and which did have major impact on performances on my case. So for the naive implementation, you really want something simple. So to have something simple, you want to avoid any kind of synchronization between threads. You want to say, okay, I have my matrix, I have my vector, and I have my output vector. And what I will say is that every single thread from my invocation will just target one particular element of my output vector. So here, what happens here is that each line here will be handled by its own thread. And you never have any kind of cooperation between your threads because you don't have to have multiple threads hitting the same box here. So on the left here, it might look a bit weird. So in WebGPU, when you will dispatch your kernel, you have two levels of threadings. So on your Rust code or your native code, you will have to specify a certain number of workgroups to dispatch. And on your kernel definition, you have to define a work group size here. So here we have n workgroups which have been dispatched. And for each workgroup, we have a workgroup size of 2. So you get 2 threads for each workgroup. Now, in practice, you won't use 2 threads per workgroup, but more like 32 or 64. But yeah, for the example, it's just 2. Now, for this naive implementation, you don't really care about this concept of threads grouped into workgroup because every thread is anyway working completely independently. So in terms of implementation on the right, this is implementation of this approach, except that it looks a little bit more complex than it should, because in this case here, we are working with a quantized matrix. So this matrix here is actually quantized with a Q8 quantization. And the thing with quantization is that a single quantized value actually represents multiple F32 values. So what happens here is that we are doing the dot product between this row and this column here. So we iterate on each column here to run the multiplication between this one and this one, this one and this one, etc. And before doing this multiplication, we actually dequantize the value from the matrix. So you can then multiply with the set of matching values from the vector. So that's why you have so many dot projects happening here for each quantized value. But in a sense, it's like the naive implementation. Iterate through the columns, sum the dot projects, and then output the result. So absolutely zero cooperation between threads. Now, let's do a smarter matrix multiplication here, where we actually don't change that much. If you look, like here we have W1 to Wn, but we also have T1, T2 here. The difference here is that we have W1 and that should be W2n. And here your T1 and RT2, instead of being on 2 rows, they will be on 2 columns of your matrix. So what happens is that your entire work group here will be operating on the same row of your matrix. So in a sense, what happens for the calculation is that T1 will compute the dot product between a part of your row, and T2 will compute the dot product between the other half of your row. So after both dot projects are calculated, what you do is that you need to take the result from T1 and T2 and you need to combine them in order to obtain your final value. And you cannot just do, okay, T1 writes into this cell and then T2 adds its value to this cell, because you might have some race condition. So you do need some coordination between both, and this is done using subgroup reduction. Okay, so this version here is an order of magnitude faster than the version right before. The question is why? Because mathematically we didn't do less operations, but the reason is that we have a significantly better memory access pattern. What happens here is that adjacent indices of threads will hit adjacent location in memory. So that would let you benefit from query-less memory accesses, which are significantly faster. Now, if you look at the code here, it's quite a bit more complex than before. But again, this is also a little bit more complicated than what it could be, because the matrix is quantized, and also because of some limitations of WebGPU. But basically what's happening here, you can ignore this part here. Like this complete block here is kind of a duplicate of this one, but with a different unpacking strategy. But what's happening here is that if you look at the local ID here, so the local ID is like T1, T2. Like 1, 2 is the local index. So you will see that within a single value of the matrix, a single quantized value of the matrix, you will see that you will have multiple threads from the same work groups reading part of the data buffer of that quantized value. Okay. So if you are working with F32, you would say that adjacent indices accesses adjacent values from the row of your matrix. For quantized value, it won't be adjacent elements from the row, but more adjacent elements from the data vector of your quantized value, just because a single quantized value is too big to be sufficiently closed in memory, so that two quantized values are sufficiently closed in memory to benefit properly from the query-less memory reads. So you do have to go deeper within a single quantized value. And here you see we do have a 4x4 matrix, because this diagram is kind of a lie, because in practice, instead of working with a single element per work group, we are actually working with 4 rows per work group. So we are effectively working on this diagram, but where each block here is a 4x4 subblock of matrix. But the idea remains the same as in here. Okay, so after you optimized your matrix modification, that's where I reached like the performances of the demo at the beginning. And because of this need to hit within each individual quantized value, instead of being able to just dequantize at the beginning, you kind of have to implement one different GEMV or GEMM kernel for each quantization times, which is a bit unfortunate. So after you have done everything we've just talked, just be aware that there are some severe WebGPU limitations, which might or might not hurt your performances, but they do make some of the implementation more complex. So first, push constants, they don't work on the web. So you do have to kind of emulate that using a cache of uniform buffers for storing your matrix sizes, because when you run matrix multiplication, you kind of have to specify the number of rows and columns. There is also the maximum storage buffer size, which by default will probably not be sufficient for running LLMs, so you do have to request a particular size. So this is based on the WGPU implementation, so the Rust implementation of WebGPU, so that may be a bit different depending on your implementation. Subgroup reduction, there are also an extension that don't work on the web. So this thing here, these lines here, reduce some, which are tied to some other piece of code that I haven't screenshot. These ones could actually be replaced by a single function call if it was supported on the web. And that one was the one that's the most difficult for me. Or that most at the time of exploring this implementation, the WGSL primitives were all 32 bits, like it didn't have a 8-bit type, like a U8 kind of type. So when your quantization format only relies on U8, you kind of have to read it as a set of U32 and then to unpack all the parts you are interested in. And that's how you end up with these things with all the unpacking. If I could have just directly used U8, then it would have been significantly simpler. And I wouldn't even have to have these two blocks. So yeah. On the web, as far as I know right now, there's no very good way to work around these limitations, at least currently. And on native, there are some extensions you can enable. And maybe you can use some conditional compilation to select your extension based on your target. But that's something I haven't done yet. And that's kind of the future work we might want to do. Because right now, the performance you saw here was on the browser, which was kind of pretty good compared to Onyx web runtime. But the native version, because the same application can run natively, so the native version is still kind of halfway below the performances of Llama CPP. So still some work to do on native for performances. And my goal here is to hopefully reach the same level of performances of Llama CPP on macOS. But when it turns to like NVIDIA graphics card, I'm less certain that we could really beat tensor cores for the matrix multiplication parts. But hopefully, if eventually I can switch to Slang, that won't be a problem anymore. So yeah, you've written your transformer. It works. You can just rejoice. So in my case, for the UI, I use the Dioxys library, which is very, very nice. It makes it very simple to write the same piece of code and have your UI work very nicely on the web, on the desktop, on mobile, etc. But of course, in this presentation so far, I only talked about GPU kernels, but all around your GPU kernels, you have everything that happens on the CPU side, which is initializing your device, instantiating your shaders, dispatching your kernels, and also just for quality of life, how do you manage to reuse your kernels across different projects? All of these questions well, they were not part of this talk, and they are addressed by something else, which is like the WGMath ecosystem. So to give a very, very quick presentation of what WGMath is about, is that the original idea is that GPU computing is very difficult. And if you look today in the scientific community, and especially the one I'm the most familiar with, which is physics simulation, it's very dominated by CUDA. Like research papers are always using CUDA, which is a bit unfortunate because it's a closed platform. It only handles NVIDIA GPUs. So the idea is to try to open this to every platform by providing more shaders that you can really reuse across projects. Because right now, especially in the web GPU ecosystem, everyone is writing their shader on their own project, but there is no real effort to share these shaders across the boundary of different projects. So I've selected web GPU. In the future, maybe I will be switching to Slang, but we see. So right now, that's what WGML look like. So what I've been presenting so far, WGML is here, this part here. This is actually based on WGBRA, which implements matrix multiplication for F32 matrices. The ones for quantized matrices is in WGML. And WG core is like a high-level library which defines vectors, matrices, tensors, so you can create, instantiate these storage buffers. And it helps you with shader composition and yeah, all the shader composition, all the shader compilation, and dispatching your kernels. So you have a bunch of other libraries, WGParry, WGRapia. You can see that the naming is not very original. I just took my native library's name and I added WG at first. So WGParry, WGRapia is for collision detection and physics simulation. So these two don't have much yet. And WG Sparkle is also physics simulation, but not for rigid bodies. Actually, I can just show something. So from the WG Math website, you also have some WG Sparkle demos here. And if I load this here, yeah, you can see the physics simulation. So this is entirely running on WebGPU. So it's kind of a sand kind of thing. And the idea here is that by having everything share the same API and even the rendering, so the rendering is from Bevy, it's also based on WebGPU. And by sharing the same API, everything here remains in GPU land. So even the communication between rendering and the result of your compute, it remains on the GPU. You don't have to read back information to just re-upload on the GPU for a different API. So you do reach a much very good performances even on the browser. And hopefully, once WG Math gets bigger and has support for more scientific domains, you will start seeing some cross-domain cooperation when you start maybe using some AI in the middle of your physics simulation pipeline, and maybe having here some sound synthesis happening on the GPU at the same time, all within the same API. Okay, so that's about it for me. Again, thank you all for being here, and I really hope that this will give you some tools if you want to get started with transformers.